Hey everybody, back here for some polar curves, part 2. Wanted to talk a little bit about slope and then area. So let's take a look at this graph below. You can see the graph of, this isn't sketched very well, but notice how I put the polar graph on the XY coordinate grid. You can see that R, this polar curve, equals 3 minus 2 sine of 2 theta. Now, when dealing in polars, in order to find the slope on a curve, for example, you can see here dy dx, right? It's easiest for us to work with slope in the context of y and x. Therefore, as we work on slope, what we want to do is we want to determine dy dx by using dy d theta and dx d theta. Now, dy d theta is found by taking the derivative of y with respect to theta. And now what we know about y is that y is equal to r sine of theta. So an expression for y in this case would be r, which is 3 minus 2 sine theta, 2 theta, times sine of theta. So if we found the derivative of that with respect to its independent variable theta, we would have dy d theta. Very similarly with x, x in terms of theta would be r times cosine theta. And hence the link between polars and rectangulars with regards to the calculus piece. Now, the next two bullets here are pretty simple to work with. A horizontal tangent, for example, on this curve, it looks like we've got a horizontal tangent, it looks like somewhere in this area. And I don't know what that value is, but I'm fairly certain that we got a horizontal tangent there. That's where dy d theta is equal to 0. Okay, so dy d theta. Now, what's interesting is that the independent variable is actually theta. So when theta equals a certain value, the y component is not changing, provided that dx d theta is not equal to 0. Okay, let's look at a vertical tangent. Okay, a vertical tangent would be where dx d theta is 0, right? Somewhere in this area, right? Which would bring about a different theta value. And I don't know what that is. Let's call that theta 1. Let's call this theta 2, right? That would be where dx d theta is 0 and dy d theta is not equal to 0. Okay, let's talk a little bit of area. Okay, so taking us back to some trig, the area of a sector. Area of a sector is theta over 2 times r squared, where theta, again, is in radians. So that's the area of a sector. But what if your radius, right? So it's pretty easy to find the area of a sector if the radius is always the same. But what if it changes, right? I could find this radius, or that area, provided that I knew this angle, central angle theta, and I knew the radius r, right? But when the radius is changing, that's when we've got a polar curve. And therefore, what we're going to do is we're still going to translate that 1/2. You can see that here. So 1/2 r squared, but we're going to integrate from theta 1 to theta 2. Right, so that could be from 0, like for example here, from 0 to, I don't know, pi over 3. What would that look like on this curve? So if I went from 0 to pi over 6, let's say that angle is pi over 6. Okay, what I'm going to be doing is calculating the area bounded inside the curve. Again, from theta equals 0 out to theta equals pi over 6. So that's how we're going to calculate area. Now, the area between two polar curves, for example, if I were to draw, I'm just going to sketch two polar curves. I'm going to do a circle, and I'm going to do a, I don't know, let's go like this. Some weird polar, right? So let's call the first one R1. Let's call the second curve R2. So this area between these two polar curves right there would be the integral, 1/2 the integral from, let's go, theta equals 0 up to theta equals pi over 4, just in this example. And again, I'm making this example up. We'll see some practical exercises here of R1 quantity squared minus R2 quantity squared. I should do that in red because I did that in red. The students like colors. Of course, that'll be integrated with respect to theta. Now, one thing that you might have to find out here, and you'll see this in a little bit, is going to be to determine where two functions or two polar curves are equal, right? So you might be given this lower bound, right? And it's pretty easy to figure out that that's theta equals 0. But then you have to find the point of intersection in order to find the area. So let's go ahead and get started talking a little bit about all of that stuff and some more. Okay, example 10, find dy dx given that x equals r cosine theta and y equals r sine theta, remembering that dy dx is dy d theta over dx d theta. So x in terms of theta is equal to r in terms of theta times cosine of theta. And y in terms of theta is equal to r in terms of theta times sine theta. So we're going to use a little product rule here. But if I took the derivative of x with respect to theta, that would give me dx d theta. Using the product rule, I would have dr d theta times cosine of theta minus r of theta times sine of theta. Now, minus because the derivative of cosine is negative sine. Likewise, for dy d theta, we would have dr d theta times sine of theta plus r of theta, or r, times cosine of theta. Now plus because the derivative of sine is positive cosine. How can we find horizontal tangents? We just talked about that. We would find where dy d theta equals 0 and dx d theta is not equal to 0. And then we would find, of course, for vertical tangents, dx d theta equal to 0 and dy d theta not. All right, so let's take an example here. It says find the slope of the tangent line when theta equals pi over 3 and r equals 1 plus sine theta. Now, I don't know what this graph looks like, but I can find dy dx. So first I'm going to find y in terms of theta. So y, of course, is r times sine theta. So y will be 1 plus sine theta times sine theta. We'll find the derivative in a moment. X in terms of theta will be r times cosine of theta. So x will be equal to 1 plus sine theta times cosine theta. All right, so I could either distribute the sign and then find the derivative. I think that's what I might do. So y is equal to sine theta plus sine squared theta. And I'll take the derivative in a moment. X will equal cosine theta plus sine theta cosine theta. I might as well have just kept it the way it was for x because I'll have to do a product rule here. Okay, so let's find dy d theta. dy d theta. That'll equal cosine theta plus 2 sine theta cosine theta. Now, shortcut, hello friend, is that sine 2 theta. So dy d theta is actually equal to cosine theta plus sine 2 theta. That might be helpful in just shortening some calculations in a moment. Dx d theta will equal negative sine theta. And then I got to do a little product rule here. I guess I'll just leave be. I'm going to do a little product rule here, so that'll be kind of messy, but I'll get cosine squared theta. And then I'll get minus sine squared theta. Ooh, that's cool. I see an identity there. Did you know that cosine squared minus sine squared? Let's see here. Yeah, that's going to be nice. That's going to be cosine squared theta minus sine squared theta is actually equal to cosine 2 theta. That's nice. Okay, so dx d theta is equal to negative sine theta plus cosine 2 theta. Cool. Oh, that's kind of interesting. Look at how those two, dx d theta and dy d theta, are kind of like each other. Fun. Okay, so dy dx. My y's are struggling right now. At pi over 3, theta equals pi over 3 is going to be dy d theta at theta equals pi over 3 over dx d theta at theta equals pi over 3. So let's do a little side work. dy d theta at theta equals pi over 3. That will equal cosine of pi over 3 plus sine of pi over 6. No, whoops, math. Do math right. 2 times pi over 3 is 2 pi over 3. That's true. So cosine of pi over 3, well, that's 1/2. And sine of 2 pi over 3, that's root 3 over 2. Okay, so together, that's 1 plus root 3 over 2. Okay, cool. I think that's right. Let's check our math. Cosine of pi over 3, 1/2. Sine of 2 pi over 3, root 3 over 2. I like it. Okay, dx d theta. I'm going to do this scratch work down here. Notice my notation. Theta equals pi over 3. That will equal negative sine pi over 3. And plus cosine of 2 pi over 3. I got that one right. I can multiply. Good for me. Okay, so as we look at that, let's see what we get. We get negative sine of pi over 3. So that's negative root 3 over 2. Okay, because the sine of pi over 3 is root 3 over 2 plus, and then cosine of 2 pi over 3 is negative 1 over 2. Uh-oh, this is going to be interesting. Maybe not. This is actually kind of cool. Okay, so this would, let me rewrite this. This would be negative root 3 minus 1 over 2. Now I'm going to put 1 over the other. So if I put 1 plus root 3 over 2 over, I'm going to plot a negative, 1 plus root 3 over 2. Ooh, that's cool. dy dx, or the slope of the curve at pi over 3 is actually equal to negative 1. That's kind of cool. All right, that's example 11. Let's continue. Okay, so area of a polar region. We kind of already talked about this, but the area of a sector we've spoken about on slides before. Theta over 2 r squared. So not a whole lot of special work there. Boom, we got theta. This is our central angle. Here's our r value. But like I said earlier, what if r is not always the same? How do we account for that, right? So let's say we're finding the area here from, this would be theta 1, likely 0, to theta 2, I don't know, that might be pi over 3, whatever. So if I wanted to find this area, of course, I got to accumulate that slightly different. So I would take 1/2, let's call that region R. So region R would be equal to 1/2 the integral from theta 1 to theta 2 of whatever the function is, right, or whatever the curve is represented by. with respect to theta. Okay, so thinking of an area like this as being swept out by a rotating ray, right? So I don't, let's see if I can, I don't know if I have the ability to do this. Maybe I don't. No, I don't have the ability. I wish I had better technology, but you can imagine that take this curve and we're just accumulating area, right? This from theta 1 out to theta 2, right? So you can imagine like kind of almost shining a light right here. And then as you rotate it, what it does is it terminates at the curve, but it accumulates area. So it's kind of cool. I probably didn't do the best job, but at helping you visualize that. But that's exactly what's going on, right? And here it looks like I'm referring to the first angle as angle alpha, right? And ending the second one with angle beta, right? So whatever, theta 1, theta 2, alpha, beta, doesn't matter. But as long as you know what you're doing there to accumulate that area. Okay, guys, I'm going to call that it for part 2. I'll get into some practical examples in part 3, doing a couple of multiple choice questions and an FRQ. So hope that went well. Let me know if you got questions on area and rates of change of polars, and we'll see you in the next video.